Today we're starting chapter 4 with section 1 and we're looking at graphs of powers greater than 2. So in this chapter we're looking at polynomial functions and we want to know how to identify whether something is a polynomial function. So a polynomial function is just an equation or a function that has non-negative integer exponents. So that means all of the terms within our function have to be non-negative, so greater than or equal to 0, and integers, so it can't have fractions, decimals, irrational numbers, and so on as exponents. So let's take a look at an example of identifying a polynomial function. So in this example, we want to determine which of the following are polynomial functions. And if they are a polynomial function, we want to find the degree. Now when we're talking about the degree is just the highest power of x for any given term. So in A, we want to know, is f of x a polynomial function? So the 2 is really 2 times x to the 0 power, and then this term here is negative 3x to the 4th power. So because this is x to the 0 and this is x to the 4th, both of our exponents are non-negative integers. 0 is non-negative, 4 is non-negative, and they're both integers. So this is going to be a polynomial function, and now we want to talk about its degree. Well, the degree is just the highest power of a single term. So this is x to the 0, this is x to the 4th, so our degree is going to be 4. So we have a degree of 4 here. B, g of x equals the cube root of x. Well, the cube root of x we can actually rewrite as a power function. So it's going to be g of x equals x to the 1/3 power. The cube root is the same as 1/3 power. So this is not going to be a polynomial function because although it is non-negative exponent, its exponent is a fraction, so it is not an integer. So not a polynomial function. For C, we want to take a look at this rational function. So h of x, is this going to be a polynomial? Well, a rational function is the quotient of two distinct polynomials. So everything in our numerator has a non-negative integer exponent, but our denominator actually is being raised to the -1 power. Anytime you have a variable in your denominator, we are not going to be a polynomial function. So this is not a polynomial function because we have our variable in the denominator. Part D, f of x equals 0. This is called the 0 function, and we do say that it is a polynomial, but this one is actually not assigned a degree. This is the only polynomial function that is not assigned a degree, and it's only for f of x equals 0. So this is a polynomial with no degree. So g of x equals 8. 8 is just a constant. This is a constant function. But remember we said, like we said in here, 2 is really 2 times x to the 0 power. So this is 8 times x to the 0. So this is a polynomial function. And the highest power of x is 0 because it's x to the 0. So this is a polynomial with a degree of 0. And the last one, f, is h of x a polynomial function? It is, because we have x to the 3rd power and this quantity to the 2nd power. It's going to give us non-negative integer exponents, but now we need to talk about its degree. Well, imagine if you took this quantity x minus 1 and squared it, so you FOILed it out. The highest power that you would get from this being FOILed is an x squared. Well, if you multiply this highest power, x squared, with this negative 2x cubed, negative 2x cubed times whatever x squared is going to be something times x to the 5th power. So when you're finding the degree of this, you take the degree here and you add it to the power of whatever is being multiplied. So this is x to the 3rd plus x to the 2nd, right? So 3 plus 2 is 5. So this is a degree of 5. So when we're talking about power functions, right, y equals x to some nth power, we're going to look at these different properties. So if n is an even integer, so 2, 4, 6, 8, 0 as well, then our graph is going to be symmetric with respect to the y-axis. It's an even function. The domain for all polynomial functions is always going to be all real numbers. Now we can only really talk about the domain because the range is going to vary. If our graph has a positive a value, then it's going to open up, right? Because imagine x squared, that's like a parabola. Our graph opens up, so our range is just y is greater than or equal to whatever our minimum value is. When we're talking about the parent function, though, it's always going to contain the points 0, 0, 1, 1, and negative 1, 1. If n is odd, if n's an odd integer, then our function is odd, meaning it's symmetric with respect to the origin. Now, with all of our odd functions, our odd polynomial functions, the domain is going to be all real numbers, and the range is also going to be all real numbers. So this is going to extend forever to the left and right, and also forever up and down. Our odd functions, right, n to the odd power, are going to contain the points 0, 0, 1, 1, and negative 1, negative 1. Now, for the purposes of when we're trying to graph these, we are going to treat all of our even powered power functions like parabolas, like y equals x squared, and all of our odd powered power functions like cubics, y equals x to the third. Now, they all have the same general shape, which is why we're going to treat them like parabolas and cubics, but as the degree gets higher, basically they just start to get a little flatter and grow a little more rapidly. So their general shape is the same, but that's why we're going to treat them like parabolas and cubics. So this is an example of one with an even integer, and this is an example of one with an odd integer exponent. Okay, so the last thing that we're going to do is we're going to try and graph the function f of x equals 1 minus x to the fifth using transformations. So this is an odd power function, so we're going to treat it like a cubic. So we're going to go over here to Desmos to take a look at how to graph this function. Alright, so now we want to try and graph this function, f of x equals 1 minus x to the fifth. And we're going to graph this using transformations. So the first thing we're going to do is we're going to graph the parent function, f of x equals x to the fifth. Now this is an odd power function, so we're going to treat it like a cubic. And remember that all of our odd power functions contain the points negative 1, 0, 0, and 1, 1. So when we graph this, right, so the first thing we're going to do is graph f of x equals x to the fifth. So when we graph that, it looks sort of like this cubic, and it goes through these points here, but it's just a little flatter here. Okay, so that's the first thing we're going to do is we're going to graph this parent function. And then we're going to do a couple transformations. So we have two different transformations we're going to do. The first transformation we're going to do is dealing with this negative. Now, before we can do this, we want to rewrite this as f of x equals negative x to the fifth plus 1, because that way we're going to be able to see it a little bit better and look at what the transformations are that are happening here. So what does this negative do to our graph? Well, this negative causes our graph to have a reflection about the x-axis. So when we when we reflect this about the x-axis, what that's going to do is it's going to change our y values. So when we graph this, we get a graph that now is reflected here. So 1, 1 became 1, negative 1, and negative 1, negative 1 became negative 1, positive 1. So this is our reflected graph. So that's our first transformation, right? We had the parent function and then we graphed the first transformation. And then the last transformation is dealing with this plus 1. So it's a plus 1 outside of our x to the fifth. So what is this plus 1 going to do to our graph? Well, this plus 1 is going to take our graph and it's going to shift all of our points on this purple graph up 1 unit. So when we do that, we're going to get this function here, And this right here is our end function. F of x equals 1 minus x to the fifth. Let me get rid of these other ones so we can have a better picture of our function. So this right here is f of x equals 1 minus x to the fifth, or when we rewrote it, f of x equals negative x to the fifth plus 1. So this is it for what we had to do today. This last example was just graphing using transformations. So you're going to be looking at doing some graphs using transformations for x to the fifth power functions, and then also for x to the fourth power functions. So remember that we treat any x to the odd power like a cubic, and any x to an even power like a quadratic, like a parabola. Alright, so good luck, and I will see you guys tomorrow.